Okay, so now we're going to start our second set of temperature notes. And what you need to do is complete that guided note sheet that was provided as you view the lecture. Now, some summary just so far, just to make sure we got the basics down. This is nothing new. Temperature is a measure of friction between moving particles. We get it. And it takes energy to move, and if you add energy, things move more, create more friction, temperature goes up. Got it. Energy to move primarily comes from the sun. Again, this idea that we're going to look at here, that there's less air up high than there is down low, means that the higher the elevation, the lower the temperature, because there's less air moving around up there. We also now fully understand that water doesn't change temperature so easy. So places near the water don't heat up and cool down as much as places that are away from the water. So a place like San Francisco, which is surrounded by that cold water in the Pacific Ocean, is pretty much going to stay nice and cool year round. Florida, surrounded by a little bit warmer water in the Gulf of Mexico, but it still is going to have a fairly moderate temperature year round that doesn't change a lot from summer to winter. And Hawaii, which is out here in the middle of the Pacific Ocean, is an extreme case. They are only changed from 6 degrees from summer to winter because the water around them doesn't change temperatures that much. However, it turns out that this effect is not the same for both oceans on both coasts of the United States. So we're going to look here and make a clarification about the East Coast versus the West Coast. And let's look at some data. First of all, San Diego in January's temperature, these are high temperatures, about 67 in July, 76. That's only an 11-degree temperature change from summer to winter. I get it, it's on the coast. But let's go over here and look at Savannah. Savannah in January is 62, but in July is 92. That's a 30-degree temperature difference. Well, both of these locations are on the water. So what's the difference? Well, let's look at another set of data just to make sure it's not just kind of weird anomaly. San Francisco, once again, very similar to San Diego, changes about 11 degrees. 58 in January, 67 in July, 11 degrees from summer to winter. And let's compare that to New York at the same latitude, but on the East Coast versus the West Coast. They have a 46-degree temperature change from summer to winter. So what we're seeing here is that the temperatures on the East Coast change differently than the temperatures on the West Coast. They actually change more. And here's the reason. The reason has to do with the direction in which air or wind moves across our country. For the most part, air moves and weather moves that direction. So if you're in San Diego or San Francisco, the air that comes to you is always coming from the nice, cool Pacific Ocean. You're always getting hit with nice, cool air. Well, if you're in Savannah, and in Savannah in the summertime, we know that this part of the country gets pretty hot. Well, as that air moves across that hotter part of the country, that air, which has a low specific heat and can get hot, hits Savannah, so it's a little bit hotter. However, in the wintertime, what do we know about this area in the wintertime? It gets cold. So as the air moves across the cold part of the country in the wintertime, it makes places on the East Coast change temperature a lot more than places on the West Coast, because San Francisco is always getting hit by air that is always the same temperature. So here's another big conclusion that you have to understand about temperatures. And this is a clarification about the water and being on the coast. Temperatures on the East Coast change a lot more than temperatures on the West Coast. Now, to clarify, a place here in the center of the country is still going to change a lot more than a place that is on the East Coast. But when we're talking about the coast, both coasts are not exactly the same and don't have the same change in temperature. Big idea that we need to understand. But now there's also another big factor that determines these temperatures from summer to winter. In general, where is it cold and where is it hot? You know this. You know that we think of the South as being hot and we think about the North as being cold. You know this to be true. Here's a graphic that shows the coldest cities, big cities in the United States, versus the hottest. And you'll notice that the cold ones are all up here. What we say they're all up north. And that the hotter cities are all in the south. And we know that to be true. We know that it's colder up north and warmer down south. The question is why? Let's look at some actual data here. And in the center part of the country, you can see the average annual temperatures. In this part of Texas, 65, and then it goes to 60 and 50. You can see these numbers seem to get smaller or lower the further north you go. So the average temperatures get lower the more north you go. Well, tying that to our review, let's talk about it. Well, temperatures measure friction, sure, which is from the air moving, yeah. Air has energy to move. That comes from the sun. Well, all of the air is sitting under the same sun, right? So shouldn't everything have the same general temperature pattern, everything else being equal? Well, here's a news flash for us. The sun is not the same up north as it is down south. And you say, wait a minute, that's the big fireball in the sky. Sure, the sun is the same. But what's different is the shape of the earth and how the sunlight hits the earth. Here along the equator, the sun comes in and hits at 90 degrees. So all my sunlight is concentrated into that area. Well, you start to get away from the equator. You get at a higher latitude, and you can actually see now the sun is hitting the earth at an angle. So it spreads out the sunlight. It's not as concentrated. And the more north you go, the more spread out the sunlight gets to be. And I can show you this with a little demonstration. Here's my little Lego figure, and I'm holding the flashlight straight up and down. And you'll notice the size of the lit area. Okay, but if I hold the flashlight over here at an angle, notice the lit area now is bigger. It's the same flashlight. So the same amount of energy is now spread out over a larger area. So the sunlight, the energy is more spread out. So any one location actually receives less sunlight. And you can see this with this little trick I do with the ruler. This is June 21st. And in Hawaii, on June 21st, the sun is coming almost straight down. You see there's no shadow there because the sunlight is all being concentrated into a small area. Now in Atlanta, though, the shadow is more spread out. That means the sun is being more spread out because we're at a higher latitude. We're on the more curved part of the earth in relation to the sun, and our sunlight is getting more spread out, and that's going to result in lower temperatures because of lower energy from the sun. Compare Atlanta versus Iceland. Iceland's way far north, and these are both taken on consecutive days. Notice in Iceland how long that shadow is. That shows you how spread out the sunlight is, even compared to someplace like Atlanta where the shadow is much shorter. And you can see that here, the sun is lower in the sky versus what it is in Atlanta. Consider these locations. Got two locations, A and B here. And you'll notice location A, the shadow is 21.2 centimeters long, but in B, it's 28 centimeters long. Which location is getting more direct sunlight? That would be A. Which location is closer to the equator? That's location A. The sun is higher in the sky there at location A, so the sunlight is more concentrated. Hence, you're probably going to have higher temperatures at A than at B because the sunlight's more directly overhead. So let's look at how the sun's energy impacts the earth and hence temperatures. Light bulb models the sun. Here's my earth. Energy is coming from the sun, hits the earth. The amount of energy received from the sun determines the temperature. Now, this is the same light bulb no matter where you are on the earth, just like it's the same sun, but we know the temperatures are different. Let's explain that using a light meter. This is a device that will measure
in the unit of lumens how much actual light you're getting, and hence how much actual energy you're getting from this light bulb. I'm going to hold it right here at 90 degrees from the light bulb, basically right at the equator, and I see that my reading is about almost 900 lumens, which means nothing. But let's see what happens as I go away from the equator. I get up here, it's dropping to 400 lumens. The same thing as I go this way. It's dropping once again to about 400 lumens. Even though this light bulb is giving the same amount of energy constantly, where you are on this globe changes the amount of energy you're receiving from that light bulb. And that's because the angle at which the rays hit the globe are different in different places. The angle here is 90 degrees. It's hitting the globe straight on, which means all the energy is directly overhead and is focused and concentrated in a very small area. As you go away from the equator and the Earth is curved, you can see that that angle now is not 90 degrees. And the sun's rays, when they hit the Earth, now get spread out a little bit more. Well, if the energy from the sun is spread out over a larger area, that means the sunlight isn't as concentrated. So you're not getting as much energy, and you're therefore going to have lower temperatures. This is a concept known as insolation. Insolation is the spreading out of the sun's energy because of the curvature of the Earth. And the farther away you get from the equator, the more spread out sunlight is, and hence the lower your temperatures tend to be.
So here's our definition for insolation. You see it's spelled. It's the spreading out of sunlight because the Earth is curved. So this explains what we knew to be true, is that locations near the equator are hotter, and that as you get away from the equator, it gets colder, and that's because of insolation, or that spreading out of the sunlight. I got you this diagram here to give you kind of a visual representation, and you can summarize what we just talked about. Location 1, when you're at a higher latitude and the Earth is more curved, sunlight is more spread out, you get less energy, your temperatures are lower. But location 2, in places closer to the equator, the sun is directly overhead, sunlight's concentrated, you're getting more energy, and you're going to have higher temperatures. So the big conclusion so far is the farther away from the equator, which is measured by latitude, that's why we introduced that in our mapping unit, the higher the latitude, the lower the temperature, because sunlight is more spread out. Once again, we can see this with the sun and the angle that it makes with these rulers. This is Atlanta on June 20th. You can see the sun's in summertime, sun's way up high in the sky. Here's Atlanta September 24th, and here's Atlanta in December. Now wait a minute, I haven't changed my latitude here. My latitude has stayed the same, but yet the concentration of the sun has changed. Here is an example of London, England in two different times of the year. Here's London in December, and notice how long that shadow is. And you can see here the angle that my ruler makes with the globe versus on June 21st, notice the angle that my ruler makes with the globe is very different. And we know that temperatures are different from December to June, from summer to winter. We can see that the sun is more spread out here in December than it is in June, and that leads to our different temperatures between seasons. So let's talk about temperatures. Why do temperatures change throughout the year? We have seasons, and the temperatures are very different, but isn't the Earth always under the same sun? I get different latitudes, but even the same latitude changes from summer to winter. And if you ask most people, they're probably going to say this because the Earth is closer or farther away from the sun at different times of the year. And you'd be partially correct. You're not wrong in saying that. But in reality, our Earth is actually closer to the sun in January. Well, that's not when we're warmest. We're warmest in June, July, August, when we're further away. So we need to explain that. What's going on that causes our temperatures to be different between seasons? First of all, let's talk about that word season. The word season is derived from a Latin word which means to sow, as in crops. So seasons were based on when it was warm enough or you got enough sunlight for plants to grow. But why does sunlight change throughout the year? It's the same sun, but it has to do with how the Earth is oriented as it's moving around the sun.
So we've been talking a lot about the difference in temperatures between summer and winter, and you guys all know that temperatures change from summer to winter. The question becomes why? What explains that? It's the same sun year round. And yeah, we know where you are on the earth because that curvature of the earth, that insolation affects how much sunlight you get and how spread out it is and what your temperatures are going to be. But aren't you on the same place in the earth year round? Your latitude, your curvature of the earth doesn't change. So why do temperatures change from summer to winter? And that's what we're going to get into here. This is the discussion of the seasons and why we have them. Take a look at our globe here. If you've never noticed, most globes are tilted. They are not straight up and down with the equator being horizontal. Our Earth is actually oriented like this in outer space. It is actually tilted at 23.5 degrees from vertical. So our Earth is tilted. Here's our sun, and you'll notice our sun is hitting the earth. As you look at this is the northern hemisphere. You can see the United States right here. And I want you to look at the part of the northern hemisphere that is lit up. This much of the northern hemisphere is receiving light. But look at the southern hemisphere. A lot smaller portion of the southern hemisphere is receiving light, because the northern hemisphere is like leaning into the sun because it's tilted that way. Well, if you're getting more sunlight, it means you're getting more energy. You're going to have higher temperatures. And we can actually prove that with the light meter again. We'll turn it on and we'll see down here at the equator, we're getting about 1400 lumens. And I'll go up to 45 degrees north and I can see I'm getting about 868 lumens. But I'll go to 45 degrees south. So it's the same curvature of the earth. It's just now we're in the opposite hemisphere. And down here now I'm getting only about 400 lumens. So even though you're at the same latitude, the same part of the curve of the earth, when the earth is tilted like this, you're actually getting less sunlight at your location. One of the tricks with the earth is it doesn't stay right here. It keeps moving around the sun. And 6 months from now, the earth is going to be oriented like this. Now, if you'll notice, our northern hemisphere doesn't have as much sunlight hitting it as it did when it was leaned into the sun. And now the southern hemisphere has a lot more sunlight. More sunlight means you're going to have higher temperatures. Less sunlight means you're going to have lower temperatures. So when the earth is tilted away from the sun, when your hemisphere is tilted away from the sun, you're in winter. When your section of the earth, your hemisphere is tilted or leaned towards the sun, you're in summer. And that's what causes the seasons. It's because the tilt of the earth is at 23.5 degrees. So some times of the year, you're leaning into the sun, you get more sunlight, higher temperatures. Other times you're leaning away from the sun and you actually get less sunlight and lower temperatures. So that begs the question, what would happen if the earth wasn't tilted? Well, look at the amount of sunlight both hemispheres are getting. It would be the same no matter what time of the year it was. If the earth wasn't tilted, we wouldn't have seasons. And everybody would have basically the same temperatures they have year round.
So how much is the Earth tilted? 23.5 degrees. That number is important. It's going to come up later. So on June 21st, the Earth is over here in this position. And to show you what it looks like, there's my globe. You can see there's my 23.5 degree tilt, and I'm leaning into the sun, at least our northern hemisphere is, and I've sketched how much the globe is lit up. And you can see there's a lot more light on this part of the globe than on this part. And you can actually see it in a map like this. You can see that there is more parts of the Earth lit up here than there is down here because the northern hemisphere is tilted into the sun.
So today is June 21st, or the summer solstice, the day where the northern hemisphere is tilted most towards the sun, and that means the sun is at its highest point in the sky. Now, I'm outside today at what's called solar noon, or that time of the day where the sun is at its highest point in the sky. Well, I have this device right here, and the sun is hitting this ruler and it is casting a shadow. The length of the shadow depends upon how high the sun is in the sky. The higher the sun is in the sky, the shorter this shadow is going to be. So we're going to measure this shadow today in the summer solstice and see what the length of that shadow is, and that can tell us how high the sun is in the sky.
And here you can see the photograph. On June 21st, the sun's not casting much shadow, which means the sun is way up here in the sky and high above the ruler makes a small shadow. So the sun's way up in the sky. We're getting a lot more intense sunlight. It's going to be warmer like we expect it to be in June. But the Earth doesn't stay there. 6 months later, the Earth is over here, December 21st, and now my globe is oriented different to the sun. It's looking something like this. And you can see now my northern hemisphere is a lot less lit up with light than the southern hemisphere. See in the picture here, there's a lot more of the southern hemisphere that is lit up by sunlight than the northern hemisphere. So with summer versus winter, we see the sun differently in the sky. It is higher or lower depending on which hemisphere we're in, and if my hemisphere is tilted towards the sun or away from the sun. There's my shadow of the ruler on June 21st, and there it is on December 21st. And that's because the sun is higher or lower in the sky, which changes the amount of energy I get from the sun. Well, there's my summer and my winter, and I get it. My northern hemisphere tilted towards the sun, I get a lot of sunlight. My hemisphere tilted away from the sun, I get less sunlight. But what about the days in the middle? What are they like? Well, on these particular points, neither hemisphere is tilted more towards or away from the sun. Both hemispheres are getting hit kind of sideways with sunlight, so they get the equal amounts of sunlight, and that is called an equinox. An equinox is the time of the year where both hemispheres get the same amount of sunlight, and you can see that here. Both north and south are getting the same length of daylight, same amount of sunlight. And it also happens when the Earth 6 months later is in this position. So we have two equinoxes and two solstices throughout the year. This is the one we're coming up on now. You can see at some point coming up very shortly, we're going to be at an equinox where the hemispheres of north and south are getting equal amounts of sunlight. The way we see the sun in the sky changes the temperatures because we get different amounts of sunlight. In summer, when it's way overhead, we get very concentrated sunlight, and you get more energy per area, you have higher temperatures. Versus in December, when the sun is low in the sky, and you're going to get less concentrated sunlight, lower temperatures. And you can see that, once again, in our rulers. You can see the different positions of the sun in the sky that gives us different amount of energy. So once again, what would happen if the Earth was not tilted on its axis? Well, we get the same sunlight year-round. We would never change. We would not have seasons. Basically, a place right here would get the same sunlight year-round. A place here would get the same sunlight. You would have one temperature at one latitude, and it'd be the same year-round.
So we've got a lot of information that I've just thrown out to you about why we have seasons and how this Earth orientation to the sun causes those seasons and the subsequent changes or patterns in temperature. So now let's summarize that information on this diagram so we have it in our notes. And what we're going to start off with here is, let's look at point A. And you'll notice that now I've got these points labeled for reference. Now I'm not going to write everything out that you're going to have to put in your notes. I'm going to talk and explain, and you'll just have to follow along and summarize this on your note sheets. So let's talk about first here about situation A. We want to describe what's special about situation A or location A. Okay, well, what's going on? And first of all, let me clarify this. We're only going to talk in reference to the northern hemisphere because that's the hemisphere that we live on. That's the one that's important to us. So at location A, what's going on? At point A, the situation is this. Our hemisphere is tilted most towards the sun, which means we get the most amount of sunlight. We're getting the most concentrated sunlight, which means our temperatures are going to be pretty warm here at A because we are tilted most towards the sun. Now, that particular day is called a solstice. A solstice, by definition, is when a hemisphere has its maximum tilt either towards or away from the sun, and that happens at these 2 points here. And we measure this, or we can tell when this happens, by where the sun is at what we call solar noon. Solar noon is the time of the day when the sun appears to be highest in the sky. So we've got point A as a solstice. My hemisphere is tilted or leaning most in towards the sun. I get a lot of sunlight. I'm going to have nice warm temperatures. Well, the Earth doesn't stay at this point. 365 days it goes around the sun, and at some point it's going to be over here at point C. Well, what's going on here at point C? Let's describe the situation at location C. Well, now my hemisphere is tilting most away from the sun. This is also called a solstice. Remember, a solstice is a day when you have your maximum tilt either towards or away from the sun. So I'm getting the least amount of sunlight here. My days are shortest, and consequently I'm going to have colder temperatures because I'm not getting as much sunlight. So I've got two things on here that are called a solstice, and that is true. There are two solstices in the course of a year. Well, the difference is one of them is the summer solstice and one of them is the winter solstice. Well, what's the difference between the two of them? A summer solstice is when you're tilted most towards the sun and you're getting the most sunlight. A winter solstice, in this case, is on point C. This is where you're tilted most away from the sun. You're getting the least amount of sunlight and you're going to have colder temperatures. So we have some seasonal names. This would be called the summer solstice, but in the news media and on our calendars, we'll see it described like this. We call this the first day of summer. Over here, my winter solstice is also commonly called the first day of winter. So these days, yes, scientifically they're called a solstice, one and the other, a summer and a winter solstice. But commonly, their seasonal names are the first day of summer and the first day of winter. Now, we got these 2 days. What's happening here at points B and D? Well, here, the northern hemisphere is getting its most sunlight. Here, it's getting its least. Southern hemisphere here is getting the least amount of sunlight. Here, the southern hemisphere is tilted towards the sun, getting its most sunlight. Very different amounts of sunlight between the north and the southern hemisphere on these solstices. However, as the Earth moves this way, northern hemisphere has more than the south. Northern hemisphere has more than the south. But we know over here the south has more than the north. As the Earth moves, there's got to be a place somewhere here in the middle where the amount of sunlight is equal. And that's what happens in points B and D. Points B and D are situations where both hemispheres receive equal amounts of sunlight. And that, by definition, is what we call an equinox. An equinox, it's right in the name there. It's equal sunlight between the hemispheres. In terms of light or sunlight, north gets more, south gets less. Here they're equal. Here the south gets more sunlight, the north gets less. Here they're equal. And this pattern repeats over and over again every year as the earth moves around the sun. Now, we do have two equinoxes, just like we have two solstices. And the question begets, well, which one is spring and which one is fall? Well, this is tough to tell. Here I can tell this is a winter solstice for me because I'm leaning away from the sun. That's a summer solstice. I'm leaning in towards the sun. The equinoxes look exactly the same between the two hemispheres because they're getting the same amount of sunlight. Neither hemisphere is tilted more or less towards the sun. So how do we tell them apart? Well, the trick is, as a snapshot in time, we can't. I can't show you this and say what equinox this is, spring or fall. Same thing with this one. What we have to know is what direction is the earth moving. I know this is summer and I know this is winter for us. Well, let's say the earth is going to move this way and we've got to designate this. If I know this is summer and this is winter, as I go this way, what must come next is fall, because after summer I go to fall. After winter I go to spring. Without these arrows on this map, I cannot tell the difference between the spring equinox and the fall equinox. Give you an example here. This is still summer, and this would still be winter. But imagine I'm on the back side of the paper. I'm floating out there in outer space, and I'm watching the Earth go around the sun from a different perspective. If the Earth were going this way, well, summer, then this is the fall, this would be winter, and this would be the spring. So we have to know which direction the Earth is moving on its orbit in order to be able to tell which one of these is spring and fall. Summer and winter are easy because I can look at this and see, hey, I'm leaned in towards the sun, I'm tilting towards the sun, getting a lot of sunlight, that must be summer. Here I'm leaning away from the sun, getting less sunlight, that must be winter. These two can only be determined by their reference to the summer and the winter solstices. So when does all this stuff happen? We know the Earth goes around the sun every 365 days or so. That means it's going to hit this particular date about the same time every year. And we know that to be true. Summer starts about the same time. It's not like one year Christmas is warm. It's never going to happen that way. So what days do these approximately happen? And I'm going to say approximately because of leap years. Sometimes the date can float a little bit one normal day to another. But this happens on or about around June 20th. My winter solstice happens about December 21st. And we know that about Christmas time, that's when winter starts. My spring equinox, somewhere around March 20th, and my fall equinox sometime around September 20th. Once again, it can be the 21st. I think sometimes it can even be the 19th, depending upon how the leap years and such work. But this gives you an approximate time as to when these particular days happen. Now, what's happening with sunlight? We want to talk about from B to C. This starts fall, and this starts winter. We know you have the least sunlight here, most sunlight here. So from B to C, what's happening in terms of the amount of daylight? Well, daylight must be going down. In this stretch, from B to C, you're getting less daylight every day. Days are getting shorter. Well, if your days are getting shorter, you know what that means with your temperatures. If you're getting less sunlight every day, that means your temperatures are going down. And you know that to be true because we're in fall in here. And you know what happens in fall. It's not hot anymore. Temperatures are going down as we go through fall heading towards winter. You know, the sun starts to set earlier and earlier every day. That's what happens from B to C. Now, what about from D to A? Well, this starts spring. And if you know you're getting the most sunlight here, least amount of sunlight here, here we're getting more daylight every day. Because every day we go this direction, we're getting closer to this day where we get the longest days of the year and we get the most sunlight. So days are getting longer. And you know that to be true. As you go through spring, we're getting out of that dark period of winter and the sun stays up later every day. Well, what happens to the temperatures from D to A? Well, this means temps are going to rise. Temperatures are going to go up because you're getting more energy from the sun, so you're going to get warmer and warmer every day. So let's talk about right now. Where are we right now? What season are we in right now? Well, we said this happens about September 20th or so. Well, is today before or after that? We're before that. This was in June. We're well after June, but we're not to this date yet. We're somewhere right here. We're getting pretty close. It's going to happen soon that we are going to switch seasons. We're going to pass this equinox. So technically, we are still in summer. We're still in this stretch, and summer doesn't end until we get to that fall equinox on September 20th. So to segue into our next question about the hottest and the coldest days of the year, we need to kind of figure out the rest of this pattern too. This is our day where we get the least amount of sunlight. This is the day where we get the most. If we're going this direction, this means in this stretch, sunlight is increasing. Well, what season is this? Well, this was the first day of winter. That's the first day of spring. That means this whole season right here is wintertime. As we go through winter, our sunlight actually increases, which means we get more sunlight every day. But we know it stays pretty cold until we get past this day here. We would expect that this be the coldest day of the year, but it's not. We know our coldest day of the year is not Christmas. It's going to be over in here somewhere. When it's January or February, that's when we get our coldest temperatures, even though technically we're getting more sunlight. The same is true as we go from point A to point B. This is my longest day of the year in June. We know our hottest days aren't in June. Our hottest days are over here in August. So we're actually getting less sunlight on this day in August, but our temperatures are actually warmer. That seems counterintuitive. You would think if it's just sunlight, this should be the hottest day of the year, and it's not. And here's why. Let me use some very simple numbers for you. And they're not exactly correct, but they're close, and they'll get you the right idea. We know that these two places here are equinoxes, and you get equal sunlight in both hemispheres. Let's say the northern hemisphere and the southern hemisphere both get 12 hours of sunlight and then 12 hours of night on these days. Well, here, the northern hemisphere, and I'll pick kind of an easy, let's say we get 16 hours of day and 8 hours of night. And I want you to think about this particular day. We've got 16 hours of daylight, which means the earth is heating up for 16 hours a day, but it's only cooling down for 8 hours. This was like our lamp with our sand and our water. We turned the lamp on, and while the lamp was on, our temperatures were going up. We turn off the lamp and we start to cool down. So if we look at this one day here, I'm heating up a lot more than I'm cooling down. Well, let's pick a day over here. Now the days are getting shorter, but let's say I'm getting 14 hours of day. Well, now I might only be getting 10 hours of night. Am I getting less sunlight than I did here? Answer is yes. But look at this one day. On this one day where I had 14 hours of daylight and 10 hours of night, think about that one day. In the course of that 24 hours, did I heat up more or cool down more? Well, I heated up more because the lamp was on for 14 hours and it was only off for 10. So it means at the end of this day, I've heated up more than I've cooled down, which means that through here, I'm still heating up more than I'm cooling down. Think about this day here. Did I heat up or cool down more at the end of the day? I did the same. So at the end of this day right here, I haven't gotten any hotter than I have gotten colder. And as soon as I move this direction, I might be 10 hours of light, 14 hours of nighttime. Think about that one day right there. I'm only heating up. The lamp is only on for 10 hours, but I'm cooling down for 14. That means on this particular day, at the end of the day, I have cooled down more than I have heated up, and I'm a little bit cooler than I was the day before. And that happens. And that happens all the way until I get back to this day. Every day in here, I have heated up less than I have cooled down, which means at the end of the day, I'm a little bit colder than I was the day before. So that's why our coldest days of the year are late in winter, not early when the sunlight is less. The same thing for our summer. The hottest days in summer are at the end of summer, not at the beginning, because we've had more days where we've heated up more than we have cooled down.
So just to reiterate, our hottest and coldest days of the year are not necessarily the longest and the shortest days of the year. Now look at this picture here. What's weird about this picture? And this was taken in June. But what you'll see here is we got leaves falling. Well, we typically associate that with fall. The trick is with this photo is that it was taken in Australia, which is our summertime. If we think about the seasons in the southern hemisphere, they are always opposite what they are in the northern. When we are tilted towards the sun, they're tilted away. So when we have summer, they have winter. When we have fall, they have spring. All of the seasons in the southern hemisphere are backwards or opposite from the northern. In Australia, Christmas is a summer holiday. They have Santa Claus going surfing because it is this time of the year where they start summer and they are tilted most towards the sun. So this time, bring me your summary sheet completed. I'll check it, and you earn your done stamp for the day.